What we're going to do today is we're going to take a look at condensed formulas, and we're going to represent that condensed formula in a Lewis structure and a zigzag structure, or a line structure. So here's a alkane, and we see that there's 1, 2, 3, 4, 5 carbons. So when we look at a condensed formula, what it's saying is this carbon is bound to that carbon's bound to that carbon, and all down the line. So if I number these carbons, often a good idea to label them, I see, hey, I need carbon 1 bound to carbon 2. And carbon 2's bound to carbon 3, 4, and 5. Now this carbon right here that I'm pointing to is carbon 1. And I also see that there are 3 hydrogens attached to carbon 1. So I draw those in. And then carbon 2, there are 2 hydrogens also attached. Those 2 hydrogens are those 2. And then there. Carbon 4 has 2 hydrogens as well. And carbon 5 has 3. If you want to double check, making sure our labels work, everything matches up. So here is the Lewis structure. Now, to draw the zigzag structure or line structure, recall that in a zigzag, we do not draw in the hydrogens. We just draw in the carbons. So I see that I have 5 carbons in a row. So all I have to do is draw a zigzag with 5 carbons. So how many carbons do I have here? There's 1 carbon, 2 carbon, 3 carbon, 4 carbon. I need a 4th carbon, or a 5th carbon. So this condensed formula can also be represented by this zigzag structure. And we can see when we count our carbons right there, we have 5 carbons. And if we double check ourselves with that zigzag structure, do we have the appropriate amount of hydrogens that are not shown? So let's redraw this zigzag here and make a comparison. So when we look at carbon 1, we see that carbon 1 right here is bound to carbon 2. Just like this, carbon 1 to carbon 2. But we know that carbons need to have 4 bonds. So at carbon 1, we would have to have 3 other hydrogens attached. Because carbon 1, as shown in the zigzag, it only has 1 bond to carbon 2. But there's 3 hydrogens that are not shown. And we see the 3 hydrogens shown there in the Lewis structure. Or we could see that there's 3 hydrogens right there. So for carbon 2, how many hydrogens should there be here? Well, if we go back to this condensed formula, we see, well, carbon 2 has to have 2 hydrogens. But if we don't have that, how many should there be? Well, because the way that we know that is this carbon 2, let's look it up right here. Carbon 2 has 1 bond to carbon 1 and 1 bond to carbon 3. So that's 2 bonds. How many bonds does carbon have to have? 4. So that means that there are 2 hydrogens that are not shown. Now, if you keep going down the line, carbon 3 would be the same thing. Carbon 4 would be the same thing. Carbon 5, though, would have 3 hydrogens. So that's the condensed Lewis structure zigzag. Now, one thing I want to mention is, do you see how I'm numbering the carbons? The way I'm numbering the carbons is just to keep track of where they are. You could label these carbons with letters or any kind of symbol. It does not matter. You're just trying to be consistent in how you identify carbons. And that way it helps you translate between the different forms of the representation of this molecule. And what is this molecule called? It's called pentane. But note this. It does not matter how you number the carbons when you're just trying to locate them and keep track of them. But the way that you number carbons does matter if you're trying to name the molecule. And we're not doing that in this video on how to naming it. So we will use the numbering rules when we want to name the molecules. But in this video, doesn't matter. In this problem here, we are now introducing heteroatoms, such as oxygen. And when you take a look at this structure, we'll just follow the same procedures. Let's convert this into a Lewis structure. So that means this carbon 1, 2, 3. So carbon 1 is bonded to carbon 2, and carbon 2 is bonded to carbon 3. Carbon 1 has 3 hydrogens. Carbon 2 has 2 hydrogens. Now, carbon 3 has something going on here. It's showing us that 2 of the oxygen atoms are bonded to carbon 3. So we could say like this, and then like this. Now, where is this hydrogen attached? Is that hydrogen attached to carbon 3? Or is it attached to carbon or to one of the oxygens? It's going to be attached to one of the oxygens. When you see that formula right there, CO2H, that is describing a carboxylic acid. And the general structure of a carboxylic acid looks like this. Like that. So this piece that I just circled is this piece right here. And the R group there represents carbons 1 and 2. So when you see it drawn like that, that means carboxylic acid. And carboxylic acids have that structure, right? So when we take a look at the generic structure, we see that this oxygen atom has to have how many lone pairs? 2 lone pairs. And this oxygen atom right here, how many lone pairs? Another 2. But this oxygen is a single bonded to the carbon, and that oxygen is a double bonded. And so I just do that in my Lewis structure. And then that would have to have another bond right there. And then how would we convert that to a zigzag? Well, the zigzag structure shows the carbons. So I have 1, 2, 3 carbons in a row. So I go 1, 2, 3. So that zigzag right there is 1, 2, 3. 1, 2, 3. Now carbon 3 is bonded to what? An oxygen atom. So heteroatoms, atoms that are not carbon or hydrogen, need to be drawn. They're not implied. So we have that oxygen right here, which is that oxygen. And we see that that oxygen has a hydrogen attached to it. Okay? And that oxygen has 2 lone pairs. But what else is also attached to carbon 3? A double bonded O. And where's carbon 3? Right here. So all we do is draw a double bonded O, like so, and they're like that. And there's the zigzag structure of this carboxylic acid. Now, could I have started my zigzag like this? Carbons 1, 2, and 3. Yes, I can. It does not matter. Because does this molecule stay in this orientation for its entire lifetime? No, molecules move around and rotate. So you can represent that rotation like this. So this representation and that representation represent the same thing. It represents this Lewis structure or that condensed formula. Both are correct and both would be okay. I now want to take a look at these two different condensed formulas, but also bring back the previous problem that we just did. Was it? Okay. It was this one right there that we did just a second ago. Remember that this one right here is the carboxylic acid. And the marker's dying on me here. So that's the carboxylic acid part. When we take a look at this one right here, this is an alcohol. And that's the alcohol part right there. And alcohols look like this, right? Generic structures like that. So there's the alcohol. And then all of this, the 1, 2, 3 carbons is the R. And then this piece right here, that is an aldehyde. Different ways to represent different functional groups. Now let's go through this one, this aldehyde first, and draw the Lewis structure. So we have carbons 1, 2, and 3. So I'll just draw those out. They're all connected. To carbon 1, I have 3 hydrogens. Carbon 2 has 2 hydrogens. And then this is the tricky one. That hydrogen, it says it's attached to that carbon. That is true. But is that oxygen attached to the hydrogen? Like a carboxylic acid? So if we draw out this guy, wait, we gotta have to have a 3 right there, H3. So in this representation, this hydrogen is attached to one of those oxygens. But now it's kind of looking a little different here. This hydrogen is attached to the carbon, not the oxygen. And this oxygen right here is bonded to carbon 3 in a double bonded fashion. So that is the aldehyde. And we could represent that aldehyde like this. There's 1, 2, 3 carbons, so we draw 3 carbons in our zigzag. And if we number them, 1, 2, 3, 1, 2, 3, we see that carbon 3 has a double bonded oxygen and then a hydrogen coming off of carbon 3, just like that. So this represents the aldehyde, but you see how this hydrogen right here is bonded to a carbon? So we don't technically have to show it. So I could represent this structure like this. Just like that. Or that's not very nice looking, is it? I'll just draw it right here for right now. So this molecule could also be represented like that. And so you would be able to look at this molecule, be like, okay, that carbon has 3 hydrogens, that carbon has 2 hydrogens. This carbon has how many bonds? 1, 2, 3. So that means it has to have a hydrogen coming off of it. So that is an aldehyde. Now let's finish this one here. 1, 2, 3. Let's just so we can look at all of them and compare. So 1, 2, 3, 1, 2, 3. There's our carboxylic acid. Now let's take a look at our alcohol. And I'm going to do this in a green marker here. So carbon bonded to another carbon, bonded to another carbon. Carbon 1 has 3 hydrogens attached. Carbon 2 has 2 hydrogens. Carbon 3 has 2 hydrogens. Now, this oxygen is directly attached to carbon 3. And that has a lone pair, 2 lone pairs. And that hydrogen is directly bonded to the oxygen atom, like that. And that is the Lewis structure of this alcohol. And when we convert that to Lewis structure into a zigzag, we count our carbons, 1, 2, 3. 1, 2, 3. And then what's directly bonded to carbon 3 is an oxygen atom. And that oxygen atom has the hydrogen and 2 lone pairs. So since that's a heteroatom, the hydrogen that is directly attached to the heteroatoms have to be drawn. This hydrogen in the aldehyde did not have to be drawn because it's attached to a carbon. But this hydrogen is attached to an oxygen, has to be drawn. It's not implied. This hydrogen is also attached to an oxygen, has to be drawn. So those are 3 functional groups that's how they look. Okay? See, that they can be kind of similar looking, but you have to be careful. They're not. Now the next one that we're going to add here is an ether. What if we had something like this? CH3, CH2. And that marker's like nearly dead. Let's try this marker here. So CH3, CH2, oxygen, CH2, CH3, something like that. So now this right here is an ether. And what do ethers look like, or their general structures? They look like this. An oxygen atom that's sandwiched between 2 alkyl groups, or R groups. So let's see if we can squeeze this in here. So we have 1 carbon, 2 carbon. Carbon 1, carbon 2, and bonded to carbon 1, 1, 2, 3, 4. Now, do you see how I'm just numbering the carbons? I could have numbered 1, 2, 3, 4, 5. I could have numbered the oxygen if I wanted to, but I don't. I don't want to. There's no need to. But so carbon 1, carbon 1, carbon 1 has 3 hydrogens attached. Carbon 2 has 2 hydrogens attached. And carbon 2 is directly bonded to an oxygen atom. And that oxygen atom is also directly bonded to carbon 3, and carbon 3 is directly bonded to carbon 4. Now, oxygen atoms, in order for them to be neutral, as it's shown in the condensed formula, because there's no charges, that oxygen atoms need, when they have 2 bonds, that means they're going to have 2 lone pairs. Carbon 3 has 2 hydrogens. Now I'm blending over into this other carboxylic acid problem here. We'll just erase it. And then carbon 4 has 3 hydrogens. And that's the Lewis structure. Now how would we do the zigzag? Let's squeeze it in right here. There's 2 carbons, so that's just a line. That's 1 carbon, 2 carbon. But we're drawing a zigzag. Carbon 2, this guy, that's carbon 2, that's carbon 1, carbon 3, carbon 4. Carbon 2 is directly bonded to an oxygen atom. See how I'm doing a zigzag there? Zigzag back up to carbon 3, and then carbon 4. And that right there is the or the zigzag structure or line structure. There's different names for these things. And there's the zigzag structure for that ether. Now let's take a look at an example with parentheses. Let's make it an alcohol. But now we are looking here, we have some parentheses here. So what does that mean? Okay. So we have carbon 1, carbon 2, carbon 3. Now the question is, do I name that carbon 4 or do I just ignore it? And based off of my numbering scheme, you can see that I'm just ignoring it. What I'm doing is I'm trying to find the longest chain or longest sequence of carbons, and I'm ignoring the ones in the parentheses. And hopefully you'll see why that is after I start drawing the Lewis structure. So I see that carbon 1 right here is directly bonded to carbon 2. Carbon 2 is directly bonded to carbon 3. Now if we ignore the parentheses, we see that carbon 3, if we ignore the parentheses, we're even there, carbon 3 is directly bonded to carbon 4. And then carbon 4 is directly bonded to the OH. That's how you're looking at it. Because the parentheses, the carbon in the parentheses is going to be attached to the carbon to its left or preceding it. So if we number these, carbons 1, 2, 3, 4, that parentheses is going to be attached to carbon 3. And so we would take that methyl group and say, okay, that carbon is going to be attached to carbon 3, just like that. And since let's actually put it down here. Okay. So the carbon in parentheses goes attached to the carbon preceding it. And now we just go through and making sure we have our hydrogens. Carbon 1 has 3 hydrogens. Carbon 2 only has 2 of them. Carbon 3 has 1. And then carbon 3 attached to the methyl, which is this carbon right here, and that has 3 hydrogens. Like that. Attached carbon 3 is directly attached to carbon 4, and that has 2 hydrogens. Like that. So how do we do the zigzag then? The way I like to look at it is I try to find the longest continuous chain of carbons. And if I start here, I could go 1, 2, 3, 4, or I could go 1, 2, 3, 4 in that direction, or I could go in this direction. And so there's a tie. So I kind of just personally like to look at it horizontally. This isn't a rule, but it's just what I like to do. I try to look for the longest horizontal carbon chain, and I see that there's 1, 2, 3, 4. So because it's just so easy to draw a horizontal zigzag. Okay. So that's carbon 1, carbon 2, carbon 3, carbon 4. And what's attached to carbon 4? The heteroatoms, like this. And then we just have to stop and like, do I have all my carbons? I'm like, well, how many carbons do I have here? 1, 2, 3, 4, 5. When I look at my zigzag, I have 1, 2, 3, 4 carbons only. So I need to like pause for a moment and be like, okay, let's number the zigzag. Maybe that will help me. 1, 2, 3, 4. So that matches. And then what do I see? Attached to carbon 3 is a methyl. And how would I represent that methyl? Just by a line. So if we clean that up without the numbers, our zigzag would look like this. Now, some people like to show the lone pairs in their zigzags. Others do not. There's really no rule that says you have to include the lone pairs. You could also draw the zigzag if you like. No major rules. You could draw the bond to the hydrogen. That's okay as well. But both of those would be acceptable zigzag structures. Now let's take a look at an example where you have the parentheses on the terminus of the molecule. So how do we do this? Starting off numbering 1, 2, 3, 4. Recall, I don't like to number the carbons in parentheses. So I'm just going to stop there. So carbon 1 is directly bonded to carbon 2, which is directly bonded to carbon 3, directly bonded to carbon 4. Carbon 1 has 3 hydrogens. Carbon 2 has 2 hydrogens. 2, 2. Now carbon 4 only has 1. But in parentheses, that means this piece, the 2 carbons, or the ethyl piece, is directly bonded to carbon 4. So I could go CH2, CH3, like that. But I'm going to expand that out. So do you see how that little piece right there is directly bonded to carbon 4? So I'm going to expand that ethyl group out, though. So there's our there. But pay very close attention now to my Lewis structure. This carbon, how many bonds does it have? 1, 2, 3. That's a problem because I'm showing carbon 4 as neutral. So that means it has to have 4 bonds. So we have to pay attention to the subscripts of these parentheses. You see how that says there's 2 of them? There's 2 ethyls. So we would have to attach another ethyl to carbon 4. And so there it is. Now when we want to convert that to a zigzag, I tend to just look at the longest carbon chain that's horizontal. There's 1, 2, 3, 4, 5, 6 carbons. So I just go. So if we keep track of the numbering system here, that's carbon 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. And I haven't accounted for those 2 carbons. And whereas this carbon is directly attached to carbon 4. So I come over here and see, okay, that's carbon 4. How many carbons are there? There's this carbon. So that carbon is that carbon. And that carbon is attached to a methyl. So I draw a methyl. So if we label these things, those guys right there, and there. And then on the zigzag, there's the 2 ethyl groups. And then this part right there is that part. So drawing zigzag structures, Just got to take it a little bit slow and just make sure you have all the pieces connected properly. Now in this one, now we have a parentheses on the other side of the molecule. And we have a nitrogen heteroatom. So we have, this looks like an amine. So now, how do you approach taking this condensed formula and drawing it into the Lewis structure? Being consistent, I like to avoid numbering the parentheses. So what we have here is carbon 1 is directly bonded to carbon 2. And carbon 2 is directly bonded to this nitrogen species. And that nitrogen has the 2 hydrogens you can draw it like this. And in order for nitrogen to be neutral with only 3 bonds, it would have to have a lone pair. Now carbon 1 here, I'm showing that it is bonded to 1 hydrogen. But in parentheses over here, it shows that I have 2 methyl groups that are directly attached to carbon 1. So we can draw our methyl, one of them right here, and then the other right here. So 2 methyls, 1, 2. So that's still carbon 1, the way I've numbered it. Okay, that's carbon 1, and that's carbon 2. And carbon 2 has what? 2 other hydrogens attached like that. Now, as I go through this, I'm always going to double check and triple check if I have any Texas carbons, or in other words, any carbons that have 5 or more bonds, or any atoms that are breaking the octet rule. So I'm always like keeping these rules in the back of my mind as I'm looking at the structures here. Now, when I look at this now to draw our zigzag, I can look and see, oh, horizontally, there's like this carbon chain right here. So I could represent, so that's 3 carbons, so just like that. And then now I have to be very careful because in my numbering scheme, that middle carbon is carbon 1, and that's carbon 2. And this carbon right here is that guy right there. But I'm making sure I'm watching and making sure I have all the connectivity. So carbon 2 is directly bonded to nitrogen with some hydrogens here. Okay. Now, do I have all the carbons? There's 1, 2, 3, 4 carbons, and here I have 1, 2, 3. So I'm like, okay, what's going on? Well, I totally missed this methyl right here. And that methyl is attached to carbon 1. That's carbon 1. So I'm going to have to come here and draw my methyl. So that one, that methyl right there is now accounted for. And that would be the Lewis structure of that amine. Now we can get a little bit more complicated now with our condensed formulas by taking a look at double bonds and triple bonds and converting those to Lewis structures and to zigzags. Okay, now this is a more complicated condensed formula here. So how do we approach this? The answer to that is following the same procedures that I've been using this whole time. Kind of ignored the parentheses, and I see there's a carbon 1, carbon 2, carbon 3. That's what I'm seeing here. Carbon 1, 3. Ignore the parentheses. carbon 4. Right? So I start off by drawing that carbon 1 is directly bonded to carbon 2. Carbon 2 is directly bonded to carbon 1. And carbon 3 is directly bonded to carbon 4. Now remember, when you have parentheses in the middle of a molecule or sandwiched between two groups of atoms, that OH preceding it, right? So if we number these carbons here, 1, 2, 4, we see that the OH is going to be attached to carbon 3. Like that. And the oxygen will have to have 2 lone pairs. Carbon 4, we see has 3 hydrogens here. Carbon 3 has this hydrogen right there. Now when I'm taking a minute and pausing, I'm like, I look at carbon 4, 4 bonds. Looks good. Carbon 3, 1, 2, 3, 4, 4 bonds, looks good. Oxygen, neutral, when it's neutral, it's going to have 2 bonds and 2 lone pairs. Looks good. We get to carbon 2, and I see that there's only 1 hydrogen. We get to carbon 1, there are no hydrogens attached to it, but we do have these ethyl groups. So that's a C to a C, so that carbon is that carbon, and that carbon only has 2 hydrogens. This carbon is that carbon, and that has 3 hydrogens. Do the same thing, because now there's that subscript right there saying that there's 2 ethyl groups. So that means we have a CH2 and then a CH3. Okay. Now, that carbon, 1, 2, 3, 4, has 4 bonds. This carbon has 1, 2, 3, 4 bonds. But carbon 1 and carbon 2 are freaking me out a little bit. Because carbon 2 has 1, 2, 3 bonds. Carbon 1 has 1, 2, 3 bonds. But when I look at the condensed formula, I'm drawing in all the hydrogens the condensed formula is showing. Carbon 2 only has 1. There it is. Carbon 1 has none. So what's going on here? Well, what we've done is that this condensed formula is representing an alkene. Because this carbon has to have 4 bonds, we give ourselves an alkene, just like that. And so that's representing a double bond. So right there, right there, that's a double bond between carbons 1 and carbon 2. And just looking at the condensed formula, you can miss that. You're like, if you're not paying attention to how many bonds the carbon atoms have. So when we go to draw the zigzag here, you could do it like I've always been doing. The longest carbon chain that's kind of more or less horizontal. So 1, 2, 3, 4, 5, 6. Right? So I'm just going to do that. 1, 2, 3, 4, 5, 6. And paying attention to my numbering scheme here, I have to understand that carbon 1, this carbon and that carbon, or this one and this one. My numbering started right here. So that's my carbon 1, and that's my carbon 2, how it's numbered here. Okay. If you want, you could maybe take this structure and go, hey, let's go 0, -1. So you can keep track of things if you'd like. Because remember, numbering is just to keep track of where all the pieces are. And then between carbon 1 and carbon 2, what do we have here? A double bond. So we draw in that double bond. Attached to carbon 2 is a hydrogen, so I don't have to draw it. But what is also attached to carbon 1? This ethyl group right there. So I have to draw that in. So down, down. So we see that this carbon right here is that one, and that methyl is that methyl. Keep going down the line. Carbon 3. That would be carbon 3. That would be carbon 4. And what do we have attached to carbon 3? We have a hydrogen that we don't draw, but we do have a heteroatom. Like that. And our methyl, carbon 4 methyl. Perfect. And so that is a representation of our alkene. Now I want to take this problem and make some minor adjustments to it and show you something, how it would change the structure. Okay? So what if I got rid of this H? Okay. And what if I got rid of that subscript 2? So now it just looks like this. How does that change our Lewis structure? So let's clean it up so you can get a better look at it. What if that was your Lewis or your condensed structure right there? CH3, CH2, carbon, carbon, CH, OH, just like that. What would change? Well, first thing that would change is that, hey, now we only have one ethyl group instead of two like before. So we can just get rid of one of those ethyl groups. Now when I take a look at carbon 1, I see it's directly bonded to carbon 2. And if I just draw it directly bonded like that, carbon 1 directly bonded to carbon 1, or carbon 2, sorry. How many bonds does carbon 1 have? 1, 2. How many does it have to have? 4. So this one would be a triple bond. And then carbon 2, shown here, has no hydrogen. So that hydrogen was never even supposed to be there. And when I look at carbon 2, I see that it has 1, 2, 3, 4 bonds. So that's happy. Then I go to carbon 3, and that has 1 hydrogen and an alcohol, and there. So that matches there. Perfect. Now, I'm going to be a little picky here, is that this is an alkyne. And alkynes, that angle right there between the two bonds right there has to be 180 degrees, which it clearly isn't based off of the way that I drew it. So I'm going to fix that. And so this ethyl group right here would come off like at 180 degrees. That. Okay. So now when we draw our zigzag structure for an alkyne, you start with the triple bond. And I like to just start drawing that triple bond like that. So that would be carbon 1 and carbon 2. And then you just extend out the bonds right here. Okay? See how they're linear? 180 degrees. And then I see that we have carbon 1, this guy, is directly bonded to that carbon, which is that carbon. And then that carbon is directly bonded to a methyl. So I draw myself a methyl. So there's our methyl. So if we want to go back to our numbering scheme like this, 0, -1, that's 0, that's -1. And then carbon 2 is directly bonded to carbon 3, which is that guy. And carbon 3 is directly bonded to carbon 4, which is our methyl. So we could say that's carbon 3, and that's carbon 4. And that would be a valid skeletal structure. You could have also drawn the skeletal structure like this. I'm going to draw it a little bit smaller. Like that, okay. That's valid. Because that's negative 1, 0, 1, 2, 3, and 4. So looking at internal alkynes, we have to understand that that is a carbon and that is a carbon. So carbon here, carbon there. That's what it's representing. Now, with most organic problems, you don't want to get into the trap of being one-dimensional. So what I mean by that is if I have this structure here, this condensed structure, you don't only want to practice how to go from here to a zigzag structure. You want to be able to be more multidimensional. Can you go from a zigzag to a condensed formula? You want to be able to do it both ways. So all the problems that I've just recently gone through, you can do it backwards. So for example, if we had a structure that looks like that, what is its condensed formula? Well, you could draw out the Lewis structure if you like, to see if that helps, or you could go directly from the zigzag to the condensed. But let's start by drawing the Lewis structure first. So I like to number carbons. There's 4 carbons in that horizontal view there. So if I draw that out, I see carbon 1 is bonded to carbon 2, bonded to carbon 3, bonded to carbon 4. And to carbon 3, there is a methyl group right there. And what do methyl groups have? Now this is the part where you have to understand and remember how many hydrogens are implied. So if I number these, how many hydrogens are on carbon 1? Well, the way I answer that question is I see that carbon 1 is directly bonded to carbon 2, so that's 1 bond. How many bonds does a neutral carbon have to have? 4 total. So that means there are 3 additional carbon-hydrogen bonds that are not shown, that are completely implied. We go to carbon 2, and I see carbon 2 is bonded to carbon 1 and carbon 3. So that's 2 bonds. So that means that there's 2 hydrogens. Carbon 3 is bound to carbon and this methyl. So there's 3 bonds. So that means that there's only 1 hydrogen. And then on carbon 4, there's only bonded carbon 3. So that means that there are 3 additional carbon-hydrogen bonds. And then this methyl right here would also have 3 hydrogens. And now from there, I see my chain of carbons. So I just start drawing this condensed formula. CH3, there's carbon 1. That's directly bonded to carbon 2, which is a CH2. Carbon 3 is a CH, because I'm just focusing on those pink numbers. And so this is in fact attached to carbon 3, but how do I show that? With a parenthesis, CH3. And then carbon 4 is CH3, like that. That's one way you could draw this structure or this condensed formula. Honestly, that looks a little weird, because another way you could have done it is you could have viewed it like this. Okay. You could have viewed it like that. There's only 1, 2, 3, and then we have 2 methyls coming off of carbon 3. So a better way to represent this would be CH3, CH2, a CH, and then we have 2 methyl groups directly attached to carbon 3. And how can we represent 2 carbons directly attached to the same carbon? Well, you would put both of those into parentheses. So you go parentheses, CH3 like that, close parentheses. But how many methyls are there? There's 2 of them. So you put a little subscript like that. So this is the best representation in that condensed formula. If you wrote this one, it gets the job done, but I've never seen it like that before. Okay. So let's tackle another one. So here's a molecule that has an ether in it and an ester. We haven't taken a look at an ester yet. So as we approach this here, let's see, we can number it like this. Let's number the oxygen this time, just to keep the numbers consistent here. Okay. So I'm trying to find the longest carbon chain here, but that longest carbon chain is kind of interrupted by these oxygen atoms. So I'm kind of just like, okay, we'll include the oxygens in this chain here. Do you see how it's not an exact science on how to number things? It's not. Now I just remember here that, hey, carbon 1 is directly bonded to carbon 2. So that means it also has to have 3 hydrogens. Carbon 2 is directly bonded to carbon 3. And it's bonded to carbon 1. So that would mean it has to have 2 hydrogens. Carbon 3 is directly bonded to an oxygen atom. So that means there's also 2 hydrogens. Oxygen is directly bonded to carbon 5. Carbon 5 is bonded to carbon 6 and oxygen 4. So that would have to mean that there's 2 hydrogens. Now, carbon 5 is bonded to carbon 6. This is carbon 6. And we see carbon 6 is also bonded to carbon 7, which is also bonded to this methyl group. Can represent it like that. So that carbon 6 right there has 1, 2, 3 bonds. So that means that there's 1 hydrogen that's implied. Carbon 7 is bonded to carbon 6 and to oxygen 8. And oxygen 8 is bonded to carbon 9. We'll get to that in a minute. But carbon 7 is also doubly bonded to that oxygen. Now when I take a look at this carbon right here, carbon 7, I see that there's 1, 2, 3, 4 bonds. So that means there are 0 hydrogens. Oxygen, carbon 9 is bonded to carbon 10, but also bonded to oxygen 8. So that means that there has to be 2 hydrogens there. Then carbon 10 would have to have, and I think I cut off, nope, didn't cut it off. Like that. So that's the Lewis structure. Now, how do I convert that Lewis structure into a condensed formula? So I'm going to show you 2 ways to do this. Okay? We could do it like this. We could do CH3, CH2, CH2. So that's 1, 2, 3, 1, 2, 3. Oxygen, CH2, CH, parentheses, the methyl group, CH3. So this carbon right here is which one? Carbon 6. So carbon 6 is that guy. That's bonded to that guy there. So that's carbon 7, CO2, like that. And so that oxygen is the two oxygens there, and that's directly bonded to a CH2 and a CH3. Now I just like double check that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 total carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 total carbons. Then I come here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total carbons. And the connectivity matches, and it looks really nice. Now, what I was going to, another way of doing this way right here, 100% correct. But you may see things like this. Do you see how there's a CH2, CH2? It's 2 in a row. You could, in theory, go like this. Let's see here. CH2 subscript 2, O, CH2, CH, parentheses, R methyl, CO2, CH2, CH3. Now that's also correct. You see, now we're just making it, simplifying it even more. Oh, there's 2 there. Let's just say it's like that. Now, in this particular case, probably you'd be like, yeah, who cares? Why go through that? Why do the parentheses there? Well, in this one, I could argue or agree with you that that's probably unnecessary, but both are 100% correct. The reason why that parentheses thing is even a thing is because you can get some really, really large molecules, and your condensed formula could be a mile long. So, for example, we could have something like this. Okay, it's not a mile long. I have limited board space, but what if, you're kind of imagining here, so what would the condensed formula look like? Well, we have a CH3 right here, and how many CH2s? 1, 2, 3, 4, 5, 6, 7, 8, 9. So what you could do is, instead of going like this, CH3, CH2, CH2. How many do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. Pretty long condensed formula, but you could make your life a whole lot easier by just going CH3, parentheses, CH2. How many are there? There's a total of 9. And then we have a OH. So this right here is the same thing as above. Just a little bit easier to write out. So if you see repeating patterns of CH2s, you can represent it in parentheses with the subscript. All right? Now, you'd be like, well, hey, I thought you said if we had a molecule like this, CH in parentheses, no. Something like that. Didn't I say that the parenthesis gets attached to the carbon preceding it? Yes, I did. But in this situation here, you have to think logically. Could you take this carbon right here, our CH3, okay? So that carbon is that carbon. Could you, in fact, attach 9 methyls, or sorry, these CH2s? CH2, 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 CH2. Do you see what I'm doing here? That's impossible because you would form a Texas carbon or a carbon that would break its octet. So yes, parenthesis, you attach to the preceding atom only if it makes logical sense, because you can't attach 9 carbons to that carbon.